awards, such as a Sloan Fellowship and an NSF Career Award. She's known for her work on non-equilibrium dynamics, ranging from formal things, how can we understand non-equilibrium closed quantum systems, to very practical things, working with experimental systems and modeling and also trying to understand them better. So very happy to have you here. Go ahead and tell us about your work.
Okay. Um, well, thanks everybody. Good afternoon. It's a great pleasure to be here. Um, so that's me. I'm Anushya Chandran, and today I'm going to tell you about work in my group from the last few years on quasi-periodic driving and try to convince you that this is a tool that could be a versatile tool in the quantum mechanics toolbox in the near term. Okay, so just to highlight this work I'm going to talk about, a lot of it was with these two people. So David Long is a senior graduate student in my group, moving on to a postdoc at Maryland next year, and Phil Crowley was my former postdoc, now a postdoc at Harvard. And then the experiments are with Alicia Kohler's group. Okay, so let's get cracking. Oops, that didn't work. Let's see. That worked. Okay, so there's a lot of buzz about quantum, right? Presumably why some fraction of you are here today to understand what this is about. So the science behind all this buzz, there are an increasing number of physical systems with an increasing number of qubits with an increasing amount of coherent control. So just to give you a concrete example in one of the experimental systems that will be relevant to my talk today.
This will go away.
It will go away? Okay. Sorry, there's so many things popping up.
I was just noticing online audience that could ask questions.
Yeah, okay. Yeah, so just to give you a concrete example for in a physical system that will be of relevance to my talk today, consider this graph from this review on superconducting qubits, one of the platforms that's being intensively worked on. So this is, on the y-axis is the lifetimes of these qubits, on the log scale, on the x-axis is time, right? And this is pretty impressive. So the earliest ones being reported from like a nanosecond lifetimes has gone up to the most recent ones, several of which are in 3 dimensions, boasting millisecond to even tens of millisecond types lifetime. So if you drew a straight line through this, you would even say it's faster than Moore's law, depending on where you drew the straight line. It certainly seems to be in line with Moore's law, right? So this is very impressive, and what does this mean in terms of the number of operations you can do, the kinds of numbers that you can do coherently, treating this like a well-controlled quantum system is on the scale of 500. But when you go from beyond 1 to several, new challenges come your way. So in particular, for example, multi-qubit operations are slower often than the single qubit ones, but maybe more importantly, it's a technical challenge. There are new sources of error. So in this particular system, it would be crosstalk. So here is an example of what you ideally want to do. So every line here represents a qubit, and the things that go across it represent operations. So something like this is something you want to do to this qubit and that qubit. This is a different operation you want to do. This is the same thing you want to do in the third qubit, etc. So this, you draw an idealized diagram like this. You're like, yes, let's go implement this on the machine. And what happens is you try to do this operation that that is implementing a change on these 2 qubits, and the third one, which is just close by in space, gets a little bit of that the action that you have done here, and so that's the crosstalk. You unintentionally affect other degrees of freedom that close by to you in space. And this is a serious technical challenge in terms of scaling up the number of degrees of freedom that you can coherently control. So this is the state of the art, at least in superconducting qubits. IBM, they have, this is the kind of thing. There are 9 layers of generic operations and 9 qubits. If you think about specific operations, you can have a few more. So this is from Google's most recent experiment. So, but this is the kind of scale they're talking about. In trapped ions, I think the numbers are similar in terms of what you can do with complete control, right? But I think that raises an interesting physical question for theorists, which is who I am. I'm a theorist. So, how can we get the most science from a few coherent qubits, which several physical systems now have, and several groups can now control. And of course, you can ask this question at two levels. You can ask it just in terms of fundamental science, new phenomena, pushing quantum mechanics, or other theories we have into new regimes. And of course, you ask this in an applied level. Is there anything interesting we can do that could be useful for certain tasks? So I want to answer both questions in the affirmative today. And the way we're going to do this has been the approach of my group the last few years, is to think about strong quasi-periodic driving of these few coherent qubits and asking what that drives you. Okay, so that's what I'm going to tell you about today to answer this question. So just to get to the meat of it, I'm going to tell you about two interesting phenomena. So the first one, we called it cavity state boosting. So here is just the setup. We're thinking about a cavity, which just to keep a picture in mind, could be, these are two mirrors, and this could be light in it. In the middle here is a qubit, which to picture it could be an atom. And it's also, there's an external drive. So this is our physical setup. And I'm going to describe to you an effect in this system, which allows the preparation of high photon number states in the cavity. And why is that an interesting thing to do? At a fundamental level, this is a part of a broader program that signals new dynamical phases in these kinds of systems, these and related systems. But at an applied level, these high photon number states are an important resource for near-term quantum sensing as well as computation. The near-term applications people talk about with the quantum hardware they have are very likely to be in quantum sensing, in which these kinds of states are the starting point to do anything interesting. Okay? And they're very hard to prepare. They're non-classical states, they're hard to prepare. So that's the first effect I'll tell you about. And the second part of the talk, I will turn around and tell you how when you drive even a single spin with multiple strong drives, you can turn it into a controlled source of noise. Again, why is that an interesting thing to do? At a fundamental level, it gives us access to studying chaos in the quantum regime, because depending on how you drive it, you can either be chaotic or not. You can sweep this whole regime and study transitions into chaos and answer several fundamental questions there. And at an applied level, I think it's an interesting experimental knob to probe heating dynamics in many dynamical experiments and simulators in which, for whatever reason, you're studying something that's heating slowly. This is either because there's scars, this is for experts among you who may have seen these things before. There's various physical settings in which dynamics can be very slow, and where what you're interested in knowing is like how the system is heating slowly, how is it heating? And people try to perform controlled experiments where they try to heat it controllably to figure this out. And that's, I think, where this kind of setting could come in and be very useful in the near term. Okay, so with that, I'm going to tell you about our main tool. How do we get these different effects? So it's going to all rely on quasi-periodic driving. So I'm going to think about systems like this and that. And when you say quasi-periodic driving, that will mean from the perspective of the qubit, which I will always represent in this talk through some kind of arrow. So it's useful to think of it as a spin, but it could also be two levels in an atom that's being addressed. So from the perspective of this spin, it interacts strongly with two or more drives. And these drives will have these frequencies, omega 1 and omega 2. In this talk, we'll take them to be comparable, but incommensurate. That's what this equation says. Incommensurate, that is that their ratio is not a rational number. Okay? So this is the strong quasi-periodic driving regime, and furthermore, these drives will have large amplitudes. This will be strong driving and incommensurate with comparable frequencies. Just to get you a feeling for what that means, let's take a picture like this and imagine we are driving the spin with a magnetic field in the x direction, which is a sum of two frequencies, omega 1 and omega 2, that are irrationally related. So you might get a curve that looks like this as a function of time. So just features to take away. You kind of see that, okay, you see some peaks. Every time you look a little bit closely, things don't repeat. right? You can kind of see it. Yeah, stuff looks a little bit different across around each peak. And the reason for that is because the ratio is irrational. Nothing here truly repeats. But the word you see, it has periodic and quasi-periodic. Why? And the reason for that is that if you look, say good things to focus on are this one and that one. If you look superficially, they look pretty similar. It looks like it almost repeats. And you look in a little bit more detail, and suddenly the features are slightly different when you zoom in and look beyond. Okay? So that's the picture you should have. We're gonna add driving that has features of almost repeating every so often, but never truly repeats. Okay. So in part one, I'll tell you about this effective cavity state boosting. What is it? And it'll give me an excuse to introduce to you the main tool that we have in this game. How do we actually analyze these kind of very strongly driven systems? There are not, there are no analytical tools that give you complete solutions, but there's a nice understanding that lets us map it to well-studied condensed matter problems and borrow intuition from there. And then I'll give you an update on the current experimental status in realizing this effect. And I'll kind of repeat the same thing with this second bit, okay? Tell you about the design and noise sources. So feel free to interrupt me any point. Okay, so in the first part, I'm going to be thinking about a system like this. I already introduced what it was, a driven cavity-QED system. And there's several experts among you, so every time you give this talk, and if you don't put up a Hamiltonian, people get upset. So up front, here's the Hamiltonian. And again, for those of you who've seen this before, it should be very recognizable. So this is the different pieces. So there's a contribution to the energy from the cavity, which is this one. This is the Jaynes-Cummings interaction. This is something that is a term that lets the qubit and the cavity exchange energy with each other. So you could de-excite one, excite the other, or vice versa. And this piece here is keeping track of the fact that there's another external drive on this qubit. What is that? So in the stuff I'm going to show you here, it looks like this. You see that there's, it's in the XZ plane. And the external drive is at this frequency omega 1, different from the cavity frequency omega 2. And just some sense of the scales. So we are in a regime where the driving is slow, and this omega 2 energy these are the lowest energy scales in the problem, and all the other coupling strands, amplitudes of the drives are larger. Okay. Furthermore, the ratio of this frequency to that is incommensurate. That's this notion of quasi-periodic driving. A comment up front, again, for those of you who've seen this before, this is actually a rotating frame Hamiltonian, which is why this scale can be the smallest scale. It's actually a detuning, not a bare cavity frequency scale. Okay, so this is our Hamiltonian, and great. It's not so far from things that people have already demonstrated in the lab. And so what's so interesting about it, right? So let me show you up front what happens when you start time evolution in the system from a state that looks like this. So the spin is prepared along the x direction, and our cavity is prepared in a particular photon number state. So for the simulations, I think we're starting it at 10. And I'm going to run this in a minute, but what it's going to show you as a function of time is what is the probability distributions of different photon numbers in the cavity as a function of time, okay? Okay, so you can see it evolving, it's changing in some way. Probably the first feature you see is that all the blue is heading off to the right as a function of time, right? You started here and the blue is all moving off there. So that's telling you you're net pumping in photons into the cavity somehow. And furthermore, you'll see it one more time, I think. Yep, you see that occasionally a blue bar just pops out? And that's telling you occasionally that all the energy that you're pumping in is recohering into nearly a Fock state, nearly a state with a single photon occupation number in it, okay? So that movie even ran a bit weirdly. And also, I find movies hard to look at. I guess that's how you know I'm not part of Gen Z. I because I'm not a part of the previous gen, whatever that is. So here's the same information laid out as a color plot. Okay, so on the y-axis is photon number, x-axis is time. We're measuring time in units of the drive period of this external drive. And the color plot is showing us what is the probability of having different photon numbers. We've put this on a log plot so you can really see a lot more variation. So black regions are where you're more probable to find photons, and white is not. You immediately see both features come out. The first is this thing we said, which is that as a function of time, when you start with the state, on average, you see that the photon number is increasing, right? So that's the first feature, and in fact, I've drawn the straight line to be precisely this value, which is something we know theoretically. We'll come to how. But on top of that is this interesting feature, which is what we call in cavity state boosting, which is that you're seeing that the distribution is kind of breathing. So it expands out, and then it just pinches again. It expands out and pinches. And the pinch points means that you are nearly a single photon number state, and that's the cavity state that we have with a higher photon number than when we started with. Okay. So why is this so interesting? It's basically an on-demand preparation scheme. It is a preparation scheme that relies, you start it, and it's something that just is controlled by the state of the qubit that this happens, and you're on demand at specific times. You're able to make a state which is highly non-classical, and I emphasize highly non-classical because it's not a scheme that relies on it being a Fock state. It also works for other kinds of cat states for the cavity that you can make. And all these kinds of states are a resource for sensing and computation, as I said before. And so this is a general purpose scheme to make them. Yeah.
So to make the cat state, do you have to start in a cat state and then it gets boosted to higher end?
Yes. Yes. Yeah, that's right. So boosting is moving whatever profile it had up in occupation space.
And if the energy is not conserved, you're probably
Yes.
repeat the question.
Oh, sorry. The question was, energy is not conserved because you're driving the system, and yes, that's the source for energy in the system. Okay, so that's the effect. That's what cavity state boosting is. So now it's time to tell you, where it comes from, and also then to give you a sense for why this is a rich place where other phenomena that we've discovered, why this is a good playground for this. Okay, so to do all this, let me just simply explain to you, pictorially construct the synthetic lattice model, which is a model of a system like this that's going to allow us to understand the dynamics here. Okay? So let's start with a related system to what I had, but physically distinct. Central, a qubit in the middle, one cavity, but we replace our drive by another cavity. Okay, so the synthetic lattice model is simply a representation of the state space of the system. Okay, so one way to represent the state space of the system is to tell you how many photons there are in cavity 1, how many photons are there in cavity 2, and at each one of these red points to tell you what is the state of the spin. If I told you all that, you have complete information about the state of the system. Right? So this is simply a representation of the state space, helpfully organized as a 2D lattice. It's because these are integer numbers, and there's 2 levels per site to tell you about the state of the spin. Okay, great. So now we can translate the Hamiltonian we may have here into what happens here to the state space to visualize it. So I'll just go through the kinds of terms you can have quickly and what they mean here. So if you had a term like this, which just acted on the qubit, well, that would just be something that acted on each site here of this lattice model. It doesn't change, it doesn't touch the cavities at all. If you had a term like this, which is something in which the cavity is excited and the qubit is excited, then what does this do? Well, in this model, it'll change the internal state of the site, and the photon number may either go up by 1 or down by 1. Okay? That's because of this A diagram here. So naturally, terms like these give you hops on the lattice. So you get connect sites nearby with like with a term like this. Now, again, for the experts among you, I've colored these hops. Why have I done that? Because I've done that to indicate that their strength is not the same everywhere. There is the classic Bose enhancement factor that tells you that the hopping amplitude to go left or right itself depends on the number of photons that you have. So going from left to right, the hops are getting stronger. Okay? Great. Same coloring, same words for the hops on the other side, telling you about the change in photon number in cavity 2 at the cost of changing the internal state. And now we're almost done. The last piece in our energetics that we should keep track of in the state space is the energy of the cavities, both 1 and 2. They're simply proportional to the number of photons. So in this space, an energy proportional to n is a linearly increasing potential. It depends linearly on n1 or n2, which I can encode as a uniform electric field. Right? Uniform electric fields give you linearly increasing potentials. So in this lattice model, I have hops in both these directions and in the presence of this uniform electric field. Okay? So that's that one last piece, and then I can tell you why is this good for. So great, we constructed a synthetic lattice model, but it was for some different system, not our driven system. And so you might say, what's that got to do with anything? And that's what's nice about this lattice. We can simply get this limit of external driving by taking a high photon number limit of our cavity. And that's just focusing on a part of the lattice which is away from the boundary here. Okay? So that's why this lattice is useful. In one lattice, it captures the physics of 2 cavities and a qubit. One cavity driven 1 cavity and 1 qubit. Or actually also 1 qubit and 2 external drives. It's all there in the same lattice, just in different bits of it. So, okay, so great. So we've simply translated the state space and the Hamiltonian here into some picture there. And you might say, why is this useful? This is the central reason why. This is why this is such an important tool for a research program, at least in my group. It's because we've taken a time-dependent problem that might be strongly driven, for which we don't have good tools, and made it a time-independent problem at the cost of adding synthetic dimensions. That's the name they go by. And once you make it a time-independent problem, we know a lot about it. In particular, the condensed matter and the modeling of materials of various types means that there are just a lot of results about what happens in lattice models, where particles can hop from one side to the other in different dimensions. The last decade has been all about understanding the effects of topological physics in these kinds of systems. So there's just a whole wealth of results to draw from. And how do we use results from here to understand what our dynamical system does? The key mapping is this. What we want to know is how wave packets behave in time in this space. And if we know how wave packets behave in time, we know what our system will do as a function of time, because we just look at the axes. However this wave packet moves tells us how the average photon number of the first cavity, second cavity, as well as the spin state would evolve in time. Okay? So that's the game. That's how we understand what's going on. Okay, so for the Hamiltonian I had up front, this is only a cartoon, but this is my last movie, and you can tell I don't have much skills at doing this. But here's what wave packets actually did. I don't know if you, well, it's not worth running again. I'll just tell you what you should have seen. There were two features. So the blob that I had in red started here, and it moved out there. Okay, so that's the net transverse motion, transverse to this electric field. So if you prepare, so it's kind of moving this way, and that's fact number 1. And observation number 2 is as it moved around, you maybe saw it, it was changing its shape, which was really, it was oscillating and breathing. Okay? So both of these features, if you prepared a wave packet in this lattice, you would see. So, okay, how does that explain what we have in our driven system? Well, this net transverse motion that you saw, it has an origin in a well-known condensed matter effect known as the Hall effect. So it is the Hall effect that predicts that this transverse velocity of the wave packet is on average quantized in units of 1 on T1. The C here is an integer called the Chern number, which we can work out. And this kind of quantization and the fact that this comes from actually it has a topological origin is a good thing, because it tells us that even if we tweak around all the parameters of this model, which for example in the real system would be tweaking the amplitudes of the drives, tweaking the couplings between the qubit and the cavity, etc. This is a robust effect so the average rate doesn't change with some regime of parameters. Yeah.
For the model you wrote down before, does it have a gauge field?
The model is in synthetic space, do you mean?
Yeah.
Yes, so it breaks in synthetic space. There are fluxes through plaquettes in that model. Yeah, so yeah, this is also kind of a thing worth noting, that we're explicitly driving the system. So we break time reversal. There's no problem. And we can get fluxes in this lattice, no problem. Sure. Ooh, at the cost of going through horrible. No, it wasn't this. I'll flash it. I'll flash it. I think it's helpful for you to see it. That's what you have. So James Cummings with so this model, when you translate it to the synthetic lattice, has a Chern number for both bands. Okay, now is where, okay, good. And get past those movies. Oh, there you go. Second chance to look at this beautiful animation. Okay, so that's the origin of this average rate, and is why we can predict what it is, and the robustness that it inherits from this lattice model analogy. Again, for the experts among you, the shape changing of this wave packet and oscillating, the origin of all that is block oscillations. In particular, that is why at some special times it comes back to the same shape. So block oscillations is an effect of wave packets whereby they oscillate and they breathe, but then at special times they recohere, come back the same times. So that's what's going on with our wave packet. It's going this way, and at special times it comes back to the same shape. Yeah.
So, so this mapping is cool. It basically maps, you retrieve all, quantum Hall physics and block oscillations that are like single particles effect, or like can be understood at the single particle level. Is there any chance that this mapping can, can map to other, interesting interacting systems? I don't know, and see something like fractional quantum Hall or.
Not obviously that I can see, because so the way I think about it is this is really, the meaning of these dimensions is really photon number n, right? And there's no notion of filling that lattice in any way. So this is these are single particle, like you can just hop in these dimensions. So you can have an interacting system that's being driven, but then I don't know how useful this description is to understand what that system does. So yeah, I don't see any, so short answer, I don't see any fractional quantum analogs by translating this. Okay, so that was the technical bit. But that was basically the reasoning, both giving you a sense for tools and where condensed matter tools come in. But this was the effect we were after, right? So we're both, by thinking about what wave packets did, we saw that the motion was such that the average photon numbers were changing in time in the way we could predict, and the pinch points are where the wave packet shape was coming back. So we can quantitatively understand why these effects, why this is going on. Okay, so that's the effect. What's the status of anybody having done this? There are various physical cavity qubit systems. And so we set out, along with Alicia Kollar's group, Martin Ritter is her senior graduate student who's actually doing all the experiments, to design and observe this effect in the superconducting circuit QED architecture. So take me too far afield to really give a introduction to it, but very, 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 oh, I guess you can't see all I see all gray in my screen, but I think you can't really see it. Anyway, so what is the superconducting qubit architecture? So very briefly, it's a solid state architecture in a very cold fridge. If you go look inside and say what kind of solid state device is, so it's made up of, there's a substrate, say for example silicon, and then there's metal on top, for example aluminum, in various strips. So the strips, where they are and the gaps, that's what defines the cavity. I think I have a, that's what defines where the cavity is. And then on the micron scale here, there is a nonlinear element known as the Josephson junction that you can make, and that's what defines the qubit. Okay? So these are microwave cavity-QED systems. And things need to be so cold because all the aluminum strips are superconducting. Okay, and so the chip that Alicia's lab has designed looks something like this to realize this effect. Here's the qubit. The particular architecture they have is known as the transmod for the experts among you. And then here you can see the picture, because these are really like aluminum lines. This is the cavity. They call it the boost cavity because this is the cavity into which they're trying to send in photons. And this is the other cavity that they use to drive as well as read out the state of this qubit. And these are for a sense of scales. The bare frequencies of these different cavities in the qubit are all in the gigahertz scale. The qubit is tunable, so you can bring it, change its frequency. And the couplings between the qubit and the cavity is also time varying, but it's on the scale, 50 megahertz to 100 megahertz scale. Okay, so that was the chip. Where are things at? The boost cavity that they've engineered is pretty high quality. I think not as high quality factor as some of the optical cavities that people have, but this is, I guess, 10 to the 5. 100,000. Pretty well isolated cavities, and they're at the point where they can engineer drives in the qubits. I'm not going to go into the details about this. This is merely to show you that they're able to apply oscillatory X and B fields as we need. All I want you to take away from these pictures is that what's being plotted in color is the qubit population. You can basically see oscillations, right? So bright, dark is a function of time, which is demonstrating coherent control of these things at various. I'm happy to go into the specific shapes and why they have it. But so the tools are there. Now it's at the point of getting all of them working together to see the effect. So stay tuned. I think they plan to have something out by the end of the year. So it's a time scale. Yeah.
So is it true that experimentalists have access to the qubit, so they could measure the state of the qubit, but they don't explicitly measure the number of photons? So it's harder for them to see what you showed us, which is in a simulation with a hopping on this on this two-dimensional artificial lattice.
Yeah.
So is there a way to measure N1 and N2 directly?
Yes, so that's a good question. So there's several ideas. So this is the next thing that once everything is working that we're gonna look at. So just to bring back a picture. So one is to simply monitor, put in a state into the boost cavity and stop driving it and monitor what it spits out, because it is a dissipative cavity. So the hope would be if there's a current source from the drive being mediated by this qubit, we should see a steady stream coming out that's telling us at what rate energy is being pumped in. So that's the first type of things we're going to do. Simply monitor what comes out when you don't drive it because of the energy transfer through this. And this is why I said low crosstalk between cavities was an important piece of that, because you don't want, again, because these physically sit close in space, you don't just want energy to go into this directly through that, having nothing to do with your qubit. So that's one idea. And there's other ideas where they can see, for low photon numbers, they can use they can detect the split. They can use the qubit itself to detect the photon number of the cavity in the dispersive region. So there's several ideas they have. I think the one we're first going to try is what I just told you. Just monitor what comes out of the cavity and see where we go. Okay, so that's ongoing. I think it's the simplest setting to see this kind of physics. But looking ahead a bit, there's theoretical limitations to this kind of setup. The important one being that it requires the adiabatic limit. Okay, so it's not something I emphasize that much, but really we're in a frame where this drive frequency, this is really a detuning, are the lowest scales in the system. And if you saw that formula for this pumping rate, it was on average 1 photon per period of this drive. Okay, so if the period of this drive is long because we had to make this kind of a small scale in the system. So in the experiments, it's a megahertz. Then you are transferring photons into this cavity very slowly, or not as fast as you could because you're relying on the separation of scales. Then, of course, at a theory level, the effect that I told you about itself does not survive indefinitely. The broader theory question of, do you need this adiabatic limit? Are there other architectures that would show this physics? And what else is out there to go beyond the adiabatic limit has been a broad program in my group for the last few years. I just wanted to flash a couple of things we've done. Happy to tell anybody who's interested in any detail. So this is a result that I think is quite interesting. It's something about telling us about seeing basically this kind of physics that we've described, energy pumps, we called it, but in the non-adiabatic limit. And we have a classification for when the steady states can show this physics, and how to predict the average photon transfer rate. So in particular, what the results here mean is that you can speed up this process significantly. One doesn't need to be in an adiabatic limit. But then these questions lead us, of course, to build models. Okay, if we have different architectures, what are good models for them? We can then turn around and study transitions out of these different steady states. Also think about the effects of interactions, interplay with disorder, also things we're thought about. So this is just a broad range of questions that it opens up once you have this combination of the synthetic lattice and the ability to analyze it away from the adiabatic limit as well. Okay. Guess I am, so I'll take another couple of minutes to give you a flavor of the second part, talking about this designer source, noise source. So stepping back for a minute, what is a noise source? Well, one way you could define it is to say, okay, here is your qubit again. There's, of course, there's always an environment, desirable or not, that always effectively affects this qubit. You can think of it as generating a time-dependent magnetic field that affects the state of the qubit. And then there's two different kinds of environments that you could imagine that the qubit sees. So I'm showing you what that environment is through the power spectrum. So that is, roughly speaking, the Fourier transform of this time-dependent signal. So if you this kind of picture here, you can't see the lines very well, but you can see these dots. It's a very spiky picture, right? So the spiky picture is telling you that in this time-dependent magnetic field, there are a few important frequencies. And most of them barely have any power. In contrast is a picture like this, where there are a few spikes, but then there's a whole broad continuum of power that you're putting in a continuum of frequencies. Right? So this is not a noise source, but this is a noise source, because the environment has a continuous power spectrum. That's the word I would say. So what is a designer noise source? A designer noise source is something that does this with some ability to design the shape of this power spectrum, and that would directly translate into ability to control the dynamics of this spin, right? Okay, so that's what I mean by designer noise source, something that puts out shapes in the power spectrum that you can control. And you might stop and be like, why on earth would you do this? Seems like a horrible thing to do. A lot of the effort in building quantum hardware and such is getting rid of sources of noise, not adding in new sources of noise. People are trying to ever more isolate their systems, not connecting to random environments that they don't know. So it seems like a strange thing to do. So what I want to argue to you is there's a particular place where I think it's an interesting thing to do, which is as a resource for controllably causing heating. So a particular place this comes up in is in the study of many-body localized systems. But in a high level, these are glassy systems. These are glassy quantum systems that relax very slowly. And it's an interesting and fundamental question as to, what are they? How do we characterize? The same questions you would hear about in a glass. Why is it relaxing slowly? How do we understand what its dynamics are? Does it have any connection to the classical glasses we know? And for all that, there's a theory, there's very active debates on how all this happens, with possibly no way to settle it, because there's no good techniques, nobody can solve it, everybody fights about it. So then you turn, of course, to what happens in the real world to try to settle it. But these, at least in very controlled platforms, are limited by their ability to cause the heating that you want to see these systems relax to. So just to give you an example, this is an experiment from Marcus Greiner's group from, I guess, it was just published last year, where they have a region this is this kind of glassy region. It's called localized. They're connecting it to a region that is thermal, which is not glassy at all. This is their source for heating, and then they're watching how this system slowly relaxes because of being in contact with this. Okay, and so I just picked out one of the plots. They have a measure of local entropy. They're watching it grow in time on different sites because of a connection to a reservoir, which is this one. This is nice, but you can see this, there's as many sites in this physical experiment as in this picture here. So it's about 12 sites, and you're partitioning them between a region that is your reservoir and a region that's your glass, and you want to study this thing. If you can get away with using 1 degree of freedom and some extra drives to function as your energy source, okay, this might be the kind of place it might be interesting into to increase the phase space we have for our system of interest. So I think the punchline here is that driven spins can act as noise sources. And this is our conjecture based on both numerics as well as analytical arguments for what it takes. So the x-axis here is the number of incommensurate frequencies that are being used to drive the spin. And what I'm demarcating here is the ability of the system to act like a noise source or not. So the takeaway from this is simply that the minimum number of incommensurate frequencies you need to make the spin, a single spin, act as a noise source is 3. Okay. And with 1 or 2, you can't. There's no regime where you can do this. Okay, so this is directly related to whether these driven systems are chaotic or not. So 1 and 2, two-tone driving, they're not chaotic. 3 and 4, they can be. Which in particular translates to their sensitivity to initial conditions. So not chaotic, meaning their dynamics is insensitive to small changes in initial conditions. Chaotic, meaning it's extremely sensitive to small changes in initial conditions. Okay. And there's near-term prospects to directly see this. One system that we were studying for different reasons a couple of years ago. This is a defect center in diamond, being driven by 2 tones. And again, as a part of doing something else, we actually saw that this system had no sensitivity to initial conditions. So what's being plotted here is the expectation value of sigma x, y, or z, depending on the color, for 2 different trajectories, prime and not prime, which are very close. So I think what was particularly being done is that the initial, there was a delay in when the drive started, which was slightly changed in between these 2 trajectories. And you can see that the difference, the spin was not very sensitive. Its change to this change in your external drive was minimal. In contrast, we run preliminary simulations with 3 drive frequencies, where now, again, same experiment. Apologies, the scale is slightly different. 2 is up here. But you can see that things grow, and the scale at which they're saturating is much larger than here. Yeah?
So this is a small question, but I expected sigma to be between -1 and 1. What is that's the magnitude of sigma here? What is sigma?
Sigma is between -1 and 1, and that's why it's not exceeding, sorry, it can be between -2 and 2, because each one can be -1, -1. Yeah, that's why the scale was -2 to 2, and things are within that. So it's the usual Pauli operators, normalized to big. Okay, so, they're much more sensitive. This difference grows, and it saturates to a larger scale. These are just preliminary simulations. I think one can definitely explore this kind of phase diagram in this system. As a function of the amplitudes of the drives, you get into this regime versus that regime. And so, we have a place to start exploring these as noise sources, and then down the line to be able to design their power spectrum.
So, so here you have one spin or two spins?
Just one spin.
One spin. So
Yeah.
what is sigma prime? Sigma I prime?
Sorry, so this is one spin started with one trajectory as a function of time, its expectation values, minus a slightly perturbed trajectory.
I see. Okay, but still, like I still don't understand entirely. So your Hilbert space is basically one qubit,
Yes.
and you want to see if you explore the full block sphere.
Yeah, so I think this is my definition of sensitivity to initial conditions. If you slightly perturb the initial state of the spin and let it go, do the trajectories diverge in the block sphere, or are they staying close? Here they're staying close. Here they're getting increasingly different.
Okay, thanks.
But yeah, so even a single spin that's driven with enough number of tones can be chaotic in that sense, like truly, yeah. Okay, so I don't have too much time, and at least part of the committee has already heard this, so I won't go into detail here. I just want to, I'll be very high level and skip a bunch of names. So really zooming out, in my research group, where we know that the organizing principles in equilibrium, everybody has that down. This is like the biggest success of condensed matter, I would say. You can even write down what it means. We have an organizing principle there. There's a free energy that's minimized, and you write that free energy in terms of order parameters. You know the right order parameters. You can capture complicated phase diagrams like this one, where all these different names are of different kinds of magnetic orders in the system. I don't know how well you can see this picture, but this is, skyrmion. It's what it's called. It's even got spins in complicated formations, but you can really get a handle on these different phases, how large are they in parameter space, how you can start to describe them just from this starting principle. And the broad research program in my group is to find that in quantum systems far from equilibrium, where it's despite almost 70 years of work, it's nowhere as mature. Nobody knows how to draw those phase diagrams, what to measure that would unify various different kinds of physically distinct systems. And we think there is a way to do that in certain settings. Is it useful? How predictive it is? That's the kind of stuff that guides this top-down approach in my group. Okay, and I'll skip this in the interest of not delving in. The other part of the research program is a little bit bottom-up, right? So this top-down organizing principles kind of question, but you can ask bottom-up, okay, can we study specific phenomena and specific interesting driven systems? Maybe that feeds into our organizing principles questions, but maybe not, and nevertheless they may have, the theory might be interesting in their own right, and they may have near-term applications in quantum science. So what I told you about today was, of course, our program in these strongly driven cavity-QED systems, doing this, exactly this, studying them their own right and thinking about their non-equilibrium phenomena. But we also study models such as these and non-equilibrium phenomena in them motivated by solid-state qubits. And a direction that's emerging in my group is to think about non-equilibrium phenomena, and particularly the ability to affect rate constants in chemical reactions by exploiting some of the physics we've learned with strong driving here and here. With that, let me thank the people in my group. Again, these two were my student and my former postdoc who really were the driving force behind most of the, almost all the work I told you about. Alicia Kolar and Martin Ritter, they're the folks we work with on the superconducting qubit experiments, and Eric and Alex Sushkov, the experimentalists working with the Diamond Defect Center. So let me thank you for your attention.
Thank you for the excellent talk. Questions? So Sohail has a question. Sohail, if you can unmute yourself, go for it. Otherwise, type it in the chat.
Yeah, hi. Am I audible?
Yes.
Okay, great. I have two questions actually. The first one is a question from one of your initial slides where you showed the movie of the photon number increasing.
Sorry.
I just want to clarify something.
Sorry, I have to figure out how. Okay, yeah. Let me go all the way back.
The next, yes, this one. So,
okay.
So you start with a photon number of 10. My question was, is there a lower cutoff where you need to start, or if you just start at 0, it keeps increasing?
Yeah, that's a really good question. So, so several things I didn't tell you about. So first is this effect happens, there's a lower and an upper cutoff in photon number where it happens. Roughly speaking, if the, it comes from this like, root n enhancement of the coupling between qubit and cavity. So if the photon number is too low, the qubit barely sees the cavity, and it's much more strongly affected by the single drive. If the photon number is too large, it doesn't see the drive, and it's only affected by the cavity. That makes sense, right? And we want to be in a regime where they're competing. So that's roughly speaking physically why there's a lower bound and an upper bound. Okay, so that said, we can move this lower bound all the way to 0. So fine. So we could start with much lower photon numbers. I think we've started with as low as 2. But so 0 itself, which would be interesting if we could just pump it up all the way from vacuum, is tricky because it's the lower boundary of the effect. So fluctuations are very important over there. And so the spin kind of fluctuates and fluctuates. It's kind of it's not a controlled way to prepare Fock states. If that makes sense. But the idea would be, sorry, just to add one thought to it. So the idea is that in terms of the particular Fock state preparation, there are schemes to prepare low photon number states. And so if you can get up to 2 or 3, which there are schemes to do, then something like this can take you up to, well, the ideal world, 20 or something like that.
Okay, thank you. Can I ask one more question quick?
Yes.
So I know this was like you're doing it a theoretical stuff, but how large a system can be built experimentally roughly with this photon number state?
You mean what are they experimentally expecting to boost until kind of thing? Yeah, okay, so the original goal of the experiment is not even to make the Fock states. They first want to just demonstrate that they're getting the energy into the cavity at the rate that's being predicted. And for the current setup, it's kind of 6, 7 photons. That's how large they are. They imagine, where the limiting factor is the Q of the cavity, basically. So beyond that, you're losing, you get into a steady state where you're losing photons at the same rate at which you're putting them in. So that's the current numbers.
Okay, thank you.
Other questions?
Hi, thank you for the talk. So regarding the Fock state preparation, you also mentioned that you could prepare coherent states. So if not from the 0 state, how do you start like preparing arbitrary or like interesting coherent states? In a sense?
Sorry, say that again. How do you prepare it in a low Fock state?
How do you prepare coherent states? Because you were saying you could prepare like cat states.
Oh, yeah. So again, this is, so the effect is boosting. So it starts with a version of the state you're after at low photon numbers, and it boosts it in Fock space. So the cat state, you would start with a cat state of 2 coherent states with low average number, and you can boost that to a higher average number. Right? So it's not solving the problem of preparation of the state at lower photon numbers. It just is a boosting scheme once you have that.
In this boosting scheme, can you comment a little bit more about what role topology is playing? Because, so at least for the block oscillations, I guess you don't need the topology to get the rephasing. So it's really for the quantized conductance, and what is that giving you, or the quantized velocity?
Yeah, that's a great question. So I think what it's giving us is, here, it's the combination of both these things that's giving boosting. Because you're indeed right. So we could have run this in a regime that has nothing to do with, not topological bands structures in the synthetic lattice, and we would get these breathing things, but around the same photon number. So it doesn't let you boost. The boosting is the fact that we have this average slope, right? Because when you rephase, you want to have had this at the same time. You wanted the weight of the whole probability distribution to have moved up in photon number space, and that's where we're relying on the fact that we have the synthetic Hall effect.
It was not quantized.
Actually, so I actually have a backup slide on this, which may be useful. Sorry, I can't skip this. There's probably a way to get out of this and do this faster. But let me show you this, which is related to your question. I often get this question, so I have this backup slide, but people are always like, what's a big deal about incommensurate drives? It didn't seem like you were using it at all. And here's a figure of merit showing you an incommensurate ratio of the two frequencies versus a 3/2, a rational approximation of this. And then I guess what's being plotted is the quality of rephasings, which is, inverse quality. Basically, we're plotting the variance of the number distribution, right, at these special times. And so the point to take away is that the variance is going down the longer you wait when you have incommensurate drives, whereas the variance is going up the longer you wait when you have commensurate drives. So to come back to your point, well, the topology is helping us because it gives us an average rate for pumping that's independent of state and stuff. So the reason the commensurate drives do poorly is because different parts of the wave packet have different slopes at which they go. Yeah.
All right, any last question?
No, that's all right. I appreciate all the questions.
Very nice talk. So this may be a angels on the head of a pin kind of question, but like I can define a rational fraction to be arbitrarily close to any irrational ratio. So how does that work? I mean, if I don't have 1/2 the golden mean or something like that, but I'm like a tiny bit off from that, I should be in the rational world. And like, are there really dramatic changes on incredibly tiny scales?
No, this is a very important question. So let me say, and a very good one. So here's how it will work out. So you notice here that I picked up, 3/2 is a pretty poor approximation of this, and you can pick better and better rational approximants, and they will often have the form P over Q, and both P and Q will become larger and larger integers. So the way to work out is that those integers themselves will set the time scale beyond which you can tell it is no longer incommensurate, and that'll be reflected in the slopes of these lines. So you'll see the slope being so small, and it'll only significant.
Great, so let's thank the speaker again. And if you want to ask any final question on her way to the airport, and now's your chance. See you.
Oh, thank you.